See, recall from yesterday that we calculated. So, if this is a renewal process, let us say non arithmetic renewal process, and I take x t z t, of course, if I am looking at the joint distribution of x t and z t, the joint distribution lies below this 45-degree line, right. And yesterday we managed to calculate essentially what is the probability of, if you put a square at x x minus x comma x minus delta, and this is z plus delta. So, this I said is probability of a t comma delta, the probability that is the probability that your duration and age the jointly lie in the square. Recall from yesterday, right, m of t minus m of t minus z, right. I am just copying from yesterday, minus m of t minus z minus delta times f x of x minus f x of x minus delta, right. This is what I got. So, this is roughly, intuitively you can think of it as describing the joint distribution between z t and x t, right, for any finite t and any delta greater than 0. So, this is true for all t greater than 0 and for all delta greater than 0. See, at a high level, if I am giving you a function r of t, remember r of t is a renewal reward function, right. R of t we took it as r of z t comma x t, reward is a function of at time t is a function of the age at time t and the duration at time t, right. So, if r is a function of z t comma x t and I know the joint distribution of z t and x t, I can calculate expectation of r t, right, because I know the joint distribution. Okay. I effectively know the joint distribution through this equation. Now, except that there are some subtleties involved that you will maybe I will show it to you on what really happens. I will show it to you by calculating expected z t or CDF of z t for finite t, okay, and then taking t to infinity. So, if you look at, suppose I want to take something like this, right, I just want to, want to keep only z t, basically integrate out x t. So, let us say I want to take that bit now, right. So, what will I do? I want to look at the probability that z is less than or equal to z t less than z plus delta, right. So, this will essentially give me the CDF of z for some finite t, right. So, this you can show is to be your what will you do, right, you know the probability that your x t z t lies in that square, right. You can add many such squares, right, over you can just add over all the x's, right. So, what you can show is that this probability that z t lies between little z and little z plus delta can be upper bounded and lower bounded. Okay. So, an upper bound you can say that this is upper bounded by m of t minus z minus m of t minus z minus delta times f x complement of z. Well, this I can write it as, this can also be written as f x complement of x minus delta minus f x complement of x, right. This is the same as that, and the same quantity is lower bounded by m of t minus z minus m of t minus z minus delta f x complement of z plus delta. See, the upper bound and lower bound come by. So, for example, the lower bound comes by summing all the these squares like till here, all right, and then there will be a little bit left here, right, which I do not know what it is. So, I take the lower bound just sums till this point, sorry, sums till this point, and the upper bound somehow upper bounds the area of this little triangle out here. Okay. That is really what you do. Okay. This is a very, I mean, this is a calculation which is just mechanical, okay, and you can get something like this. This is not, I mean, this is not very difficult to believe at the end of the day. So, now what do you have? Suppose this delta is fairly small, you have upper and lower bounds on the probability that z t lies in z to z plus delta, correct. From this, can I not get the CDF of z of t for any finite t? I can just sum, no, I can again sum this, right. So, if you do that, from this we can show the following, okay. Can calculate probability that, see, the mechanics are little subtle, but you can calculate this, and what it comes out is a sum like this. I think you can, if I write it down, you will see that you can believe it. You will get something like this, probability that z t less than or equal to little z is upper bounded and lower bounded like so. You will sum over all the z's, right. You will sum L is equal to 0 to k is equal to 0 to L minus 1, m of t minus k delta minus m of t minus k delta minus delta f x complement of k delta. Times f x complement of k delta plus delta. What I am essentially doing is I am summing over, see, I have a handle on the area, I mean the probability mass under a strip like this, right. So, now I am further dividing this into several other delta strips like that, right, and I am summing all these areas, okay, and then I have this lower bound and upper bound. Okay. Now, if I send say delta to 0, what happens is the question, right. I have this, I want to take probability of z less than or equal to z and bound them between these two sums, and I send, let us say, send delta to 0. Okay. Now, what happens to these sums? That is the question. Okay. The answer is that these sums that I have put out, which are lower bounds and upper bounds to this CDF of z of t, these upper bound and lower bounds, when I send delta to 0, they approach certain integrals. Okay. In fact, these can be shown to be lower sum and an upper sum corresponding to a special kind of an integral. It is not just a Riemann integral, it looks like a little bit like a Riemann sum, except that in a Riemann sum you will have something like f x. So, f x complement of k delta times delta itself, right. Instead of delta you are having m of, this is some m t. So, this is like a difference of two functions, right. If this term were just delta in the upper sum and the lower sum, you would just write it as a Riemann integral, correct. This is not just a Riemann integral, this is known as a Reimann-Steiltjes integral. Have you heard of a Steiltjes integral? This is what it is. If you send delta to 0, you are basically integrating a function f x, f x complement in this case with respect to some function m tau, okay, or m t in this case, right, m t minus tau or whatever. Okay. So, instead of just delta, you take m as the identity function, for example, you will have Riemann sum, but m is not identity, m is some function, you will get the so called Reimann-Steiltjes integral. Okay. So, these are upper and lower sums of a Reimann-Steiltjes integral. See, whenever I write, see, even in I mean I have written some sort of thing like this before, right. If when I write integral some function g of x d f x, that is also a Steiltjes integral technically, right. It is not just dx, right, d f x I am writing. So, this is like a this is a Steiltjes integral. Okay. In fact, what happens is that you will get, so now you send delta down to 0, you will get probability less z t less than or equal to z will be equal to integral f x complement of u d m t minus u, where u goes from 0 to z. Okay. Or which you can again write by putting t minus u as some tau. See, this is what I mean, you can look at, you can read this off, right. This is looking like f x complement of some u, k delta is the u variable. So, I am putting t minus u, this is like d, it is not du, but d m u, m t minus u. Okay. That is what, this is the definition of this Reimann-Steiltjes integral. It is the, if the upper sum and lower sum converge to the same amount, same thing, it is the integral. Okay. This is like a generalization of Riemann integral, that is all there is. Okay. And if you just change this variable, this becomes integral tau equals t minus z to t f x complement of t minus tau d m tau, is that correct? So, I have just put t minus u equal to tau, which means t minus tau is u, that is correct, and u goes from, u is 0 means there will be a negative sign which counteracts, yeah. So, this is probability that z t less than or equal to z. Okay. Let me just check, f x complement t minus tau d m tau, correct. Okay. So, this is what it is. So, this is the CDF of z t for any finite t, this is true for all t. Okay. You give me, I give you t is equal to 2.5, you tell me what the CDF of z t is, I can go calculate this Reimann-Steiltjes integral and give you the answer. Now, I need to integrate with respect to m tau. How do I find m tau? Renewal equation, Laplace transform, whatever we have studied this, right. You can use Laplace transforms or just solve the renewal integral equation somehow, put m tau into this and solve. So, you can in principle get this. Okay. Now, the question is, how does this behave as t tends to infinity? Okay. So, these questions will be answered by the key renewal theorem. Okay. Similarly, if I want to calculate, let us say this is just the CDF of z of t, right. Suppose I want to calculate expectation of z of t. See, the earlier CDF is expectation of indicator z less than or equal to little z, right. Suppose I want to calculate expectation of z of t, this is another, this is for finite t, right. I am not taking t to infinity yet. Okay. So, this is this of course, the previous answer, how does this behave as t tends to infinity will be given by key renewal theorem, which I will state in a bit. So, similarly expectation of z of t you can write it as follows: z of t is the age at time t, right. So, there are two possibilities now. Okay. The first possibility is that there has been no arrivals till time t, no arrivals at all, no renewals at all, which means the age will be equal to t, right. So, with probability, what is the probability that there has been no arrivals till time t? Probability that x 1 greater than t, which is f x complement, right. So, with probability f x complement of t, z of t will be t, okay, plus there is other possibility that there have been renewals, right. For this you have to write out an integral, okay. This again is done in your book. So, you have to take upper bounds and lower bounds, right. So, you will get this will roughly be like some again some sort of a sum k is equal to 0 to L minus 1, you are dividing it to delta delta intervals, okay. It will be like k delta, which is the value of the age, times probability that. So, this is the probability that x 1 greater than t, okay. Probability that k delta less than or equal to z t less than k delta plus delta, and this we already know what it is, right. So, this will be like t f x complement of t plus something that looks like k is equal to 0 to L minus 1 k delta times this we already know, right, m of t minus k delta minus m of t minus k delta minus delta f x complement of k delta. So, I am just substituting this guy from here, right. I am just putting this here, okay. Now, again, so this when I write this approximately equal to, I mean that I can upper bound lower bound just like I did for f x complement, okay. Now, you send delta to 0, okay. Now, what will the sum become? What kind of an integral will it become? It will become another Reimann-Steiltjes integral, okay. So, bottom line is you can show that expected z t, the first term will be the same t f x complement of t. I think Gallagher's book is missing this t, okay. Just please take it out, I think there should be a t here, plus integral t minus tau. So, this will be like u f x complement of u d m t minus u, right. So, this will become similarly it will become t minus z to t minus tau m of f x complement of t minus tau d m tau, okay. Similar sort of a calculation, just the Reimann-Steiltjes. So, this is like, so this is another Reimann-Steiltjes integral, you go ahead and find m tau, put it in, for any finite t you can get this expectation of z of t, okay. So, we can get CDF, we can get z of t, the expectation of z of t for any finite t, okay. Now, again the question is how does this behave as t tends to infinity? See, if t tends to infinity, the first term will, see the first term will, you can imagine, will go to 0, okay, because f x complement of t is going to 0 and it even has finite expectations, you can, so take t times f x complement of t will also go to 0. Now, the first term will go to 0 and the second term, what does it go to is the question. Similarly, in this expression also, right, we want to know as t tends to infinity what does this integral go to. Intuitively, what does this m tau, right, what does this behave like? See, m t over t for large t behaves like 1 by x bar, right. So, m t has t by x bar plus a bunch of other terms, So, d m tau should behave like 1 by x bar, correct. D m tau should behave like d tau by x bar, correct. So, that is what you would expect and that is what is true, okay, under some technical assumptions. So, that is what key renewal theorem says. So, the key renewal theorem lets us take t to infinity in the above Reimann-Steiltjes integrals. It says key renewal theorem, let r of x be a directly Riemann integrable function and let mt be equal to expectation of nt for a non arithmetic renewal process. Then limit t tends to infinity integral tau equal to 0 to t. So, sorry I think I made a mistake. So, this should be 0, please correct this, 0 to t, okay. I made a mistake here, please correct that. So, tau is equal to 0 to t, r t minus tau d m tau is equal to 1 over x bar integral 0 to infinity r of x dx. Okay. So, if you look at let us say this integral here, right, that is looking like integral 0 to t some function, let us say this could be r of t minus tau, right. You are looking at the integral 0 to t r of t minus tau d m tau. In this kind of an integral I want to send t to infinity, I want to know what happens. Key renewal theorem tells you what happens, okay. Key renewal theorem says if r of t, r of x, little r of x, okay, is any directly Riemann integrable function, then this kind of an integral limit t tending to infinity r t minus tau d m tau is simply 1 over x bar integral 0 to infinity r of x dx. Now, I have to, I will tell you two things. One, I have to tell you what directly Riemann integrable is, right, it is just a technical assumption, and then I will just give you a very basic interpretation of this theorem, okay. I am not going to prove this, this is a non trivial result to prove, okay. This actually comes from Blackwell. So, if you look at this, what is directly Riemann integrable? You know what Riemann integrable is, right. So, if I want to integrate a function r of x, little r of x from 0 to b, I divide the x axis into small delta intervals, take the upper Riemann sum, take the lower Riemann sum, send delta to 0, I get integral 0 to b r of x dx. So, if I want integral 0 to infinity r of x dx, I first calculate integral 0 to b using this division and then send b to infinity, right. Such a that is, so you have Riemann integrable and then you send b to infinity, okay. But if you were to partition the entire 0 to infinity using delta intervals and take upper and lower Riemann sums, if the upper and lower Riemann sums for the entire 0 to infinity interval converges, then such a function is said to be directly Riemann integrable, meaning that you do not go from 0 to b and then send calculate the integral and then send b to infinity, you directly write a Riemann sum for the entire semi infinite interval, okay. What you can show is that directly Riemann integrable functions are always Riemann integrable, but not vice versa. So, directly Riemann integrable is a little stronger than Riemann integrable, but nevertheless it is not too strong a restriction. So, if r of x is a nice enough function, d m tau behaves like d tau by x bar, that is all this is saying in the limit. So, this guy behaves like d tau by x bar, right, that is what we are getting, correct. There is a one way x bar outside, right. Yeah, so the question is are there examples of a function which is Riemann integrable, but not directly Riemann integrable. Your book has an example, exercise 5.28 apparently, it gives an explicit example, but these are really, I mean, these are just technicalities. All I want to know what happens when I send t to infinity, that is my question. Okay. So, using KRT, so if I want to take limit t tending to infinity in z of t, right, what will I get? So, limit d tends to infinity expected z of t equal to what? The first term goes to 0, right. Thus, for the second term I can use key renewal theorem, right. So, this is my r t minus tau. So, I can simply write down the answer as 1 over x bar integral 0 to infinity r of x is x f x complement, simple, right, x f x complement of x dx. You have to show that x f x complement is directly Riemann integrable. Okay, it is, take it from me that it is.
It should be x bar, not by x
bar. Correct? Sorry. Now, what is this integral? Integral x f x complement of x dx. It is yeah. So, you can show that this is equal to expectation of, you can do integration by parts. You can just do integration by parts if you want. So, this will be the answer, of course, we always knew, right. This answer we knew should be the case. Why? Time average we know the answer. Just to get this answer involved, you know, calculating this Steiltjes integral and then invoking this big hammer called key renewal theorem. Okay. So, that is, so the bottom line in all this is that the for non arithmetic renewal processes, limit t tending to infinity of expectation of r of t. So, this here r of t is just z of t, right, will be expectation of r n over x bar. Okay. But to get this, you need to go through these Riemann-Steiltjes integral and then apply key renewal theorem and all that. Okay. So, likewise you can just similarly you can write limit t tending to infinity f z t of z is equal to, you can write it as 1 over x bar integral 0 to z f x complement of x dx. I am going back to this guy now, I am going back to this, right, and I am now taking r of t minus tau is f x complement of t minus tau, right, and I am, instead of going from 0 to t, I am going from t minus z to t, right. And so, if I apply key renewal theorem, I will get an integral like this. This is integral 0 to z f x complement of x. Okay, but this also I already knew. So, these are all answers that are not surprising, but the method is through this Riemann-Steiltjes and then putting down this key renewal theorem and coming to this. So, now again, so we can do this for any reward function. Reward function r of t is r of z t comma x t, right. I can write down, see, I know the joint distribution of x t and z t for all practical purposes, right. So, I write down this Riemann-Steiltjes sum, send delta to 0, I will get some Steiltjes integral, then invoke key renewal theorem. So, if in general, if r of t is equal to r of z t comma x t is a renewal reward function, you can write out, I will not again dwell on this too much, but you can write expectation of r of t is equal to integral x is equal to t to infinity r of t comma x d f x of x plus integral z is equal to 0 to t x is equal to z to infinity r of z comma x d f x of x d m t minus z. Okay. So, the again this term corresponds to age is equal to t, meaning there has been no renewals, okay, which is why I am putting z is equal to t, right, and then I have x has to go from t to infinity r of t x d f x. Okay. This is like we wrote down t times f x complement for expected z of t, right. So, this first integral corresponds to there being no renewals until time t. The second integral is a Reimann-Steiltjes integral. You have to write r z x and then you have to sum out, you had this probability of being in a small delta square, right. You will just have to write that out as a Reimann-Steiltjes integral. Okay. The method is the same if you just look at what I did for expected z t, right. So, I wrote down this big sum out here, right, out here. So, the same sort of a thing you can do for I just did it for z of t, you can do it for any r of z of t comma x of t, right. You can then you will get this kind of a result. Okay. So, this is for any finite any t greater than 0. Now, how do we send t to infinity using what theorem? Key renewal theorem. Okay. So, if you take limit t tending to infinity expected r of t, what can be shown is that this guy will go to 0 if r of if this you will see why. See, if you look at this guy, this is the function. So, if you look at this bit, if this bit is so this is just a function of z, right. So, if this bit is directly Riemann integrable, then I can use key renewal theorem, right, and if that is the case, this this term will go to 0, the first term will go to 0 and I will get what will I get? I will get 1 over x bar integral z is equal to 0 to infinity little r of x dx, where my little r of x is z to infinity r of z dz. So, it will be x is equal to, so r of x z x d f x of x dz. Okay. This is by key renewal theorem. Okay. I am going from here to here by key renewal theorem, by taking this inner integral as my r of the little r function. Okay. But again, if you go back to your time average reward processes, this is exactly what we got. You remember this this was a while ago, but if you remember, we calculated limit t tending to infinity 1 over t r of integral 0 to t r of tau d tau. This is exactly what we got. Okay. So, bottom line is that for non arithmetic processes, the answers are the time average reward and ensemble average rewards are numerically the same. Okay. Time average rewards were very easy to calculate using strong law of large numbers. Ensemble average rewards requires a lot more subtlety and lot more machinery. So, in particular, you have to find out the joint probability distribution of f of z t x t by looking at that little square, right. Then for calculating any expected r of t, which is r of z t comma x t, you have to sum over all the probabilities of the little squares. These sums become Reimann-Steiltjes integrals, right, correct. So, that much is just calculus. then for going from that Riemann-Steiltjes integral with respect to dmt, going to just a plain old Riemann integral requires this key renewal theorem. But if you do all this, finally the answer you get is what you want, which is reassuring, right. So, that is really all you need to know. I think for all practical engineering purposes, in the vast majority of cases of interest, you will have directly Riemann integrable little r, and you will have ensemble average reward is equal to time average reward. Okay. But just in case you are doubtful, you know where to look. That is why, so the purpose of this lecture is to not so much to tell you that the answers are the same. Of course, the answers are the same between ensemble rewards and time average rewards. It is roughly to tell you how it goes, right. I have not proved anything rigorously. So, that if in your research, if you find some technical subtlety, you can check for direct Riemann integrability, or you go back to the Riemann-Steiltjes integral, right, just in case you have this problem. Okay.